Hi everyone, my name is Nir, and I'll present our work Open Vocabulary Semantic Segmentation using test-time distillation. This is a work with Yedid Hoshen, and we are from the Hebrew University. First, let's have a short brief on semantic segmentation. Semantic segmentation is about assigning each pixel in a given image a semantic label, where the semantic label, the class category, is usually taken from a predefined set of classes. For example, we can see here an image that is taken from a camera placed on a car, and we want to classify the pixel here to be classified as road, sky pixels, car pixels, etc. Usually, it is much difficult and more expensive to obtain pixel level annotations than image level annotations. In the scenario of supervised semantic segmentation, for every class category that we want to segment, we need to first collect images which contain pixels with the same semantic labels. We need to annotate these images, and then we usually want to use some deep network or any other data-hungry algorithm to learn how to classify the pixels and segment the image. This process is costly, time-consuming, and tedious, and especially for use cases where new categories are always needed to be segmented and new categories are requested from time to time. Also, supervised semantic segmentation, we cannot handle well class categories which are rare, do not exist, or other unique visual concepts such as landmarks. Moreover, current supervised methods do not scale well to work on imbalanced datasets of large vocabularies, where common categories have many examples, while the rare categories follow a long-tail distribution. To overcome the scarce annotations issue, different paradigms have been proposed over the years. First, few-shot segmentation and weakly-supervised semantic segmentation have been proposed, where the amount of supervision is different. First, for few-shot semantic segmentation, we have few images which are fully annotated, and usually it's less than 10 images. And in the scenario of weakly supervised semantic segmentation, we have typically a larger dataset, but it contains segmentations, it contains annotations which are not pixel level annotations, but some sort of other annotations. Typically, it is image level labels, bounding box, or scribbles, as can be seen below, where image level labels are probably the most popular form of weak supervision due to their simplicity and ease of obtaining them from public dataset or web-based data. Lastly, the paradigm of zero-shot semantic segmentation have been proposed, where zero-shot semantic segmentation method use zero-shot learning at the level of individual pixels. These approaches learn a training time to classify pixels into a closed set of class categories, and then at test time, we want to apply these models on never seen class categories. In our work, we propose a computationally lean method for segmenting objects that do not require new data annotations and achieve high accuracy results. The input to our method is an RGB image together with prompt categories that we want to segment, and then eventually we output a discrete segmentation map. Our pipeline consists of two main stages. The first stage is about creating high-quality relevance maps. The second stage is about integrating the relevance map into single-image segmentation methods. How we create the relevance maps? We distill information from the transformer model of CLIP in order to generate the relevance maps. CLIP is a vision language model that embeds visual and linguistic concepts into a shared latent space via large-scale contrastive learning on web-scale data. How we create relevance maps? So the input is an RGB image. Next, we take and generate multiple augmentations of the image, multiple views. Then we use clip transformers with the explainability method of Schaeffer et al., which generate a relevancy map for each query category, where the query category is being chosen by the user, where he or she can choose what objects they wish to segment. Then we use test time augmentations. We use test time augmentations to generate the averaged relevancy map, which is usually of higher quality. Here we see a representative example of generating relevancy map and the final segmentation output. For example, we can see here on the first row query category of house, person in red, doll, or tree. And on the columns till the fourth column, we can see different augmentation, different views of the image, and the output relevance map. On the fifth column, we can see the merge relevance map, which is obtained by averaging the four relevancy map and therefore reduces noises and errors. Then we combine the merge relevance maps into a multi-class relevance map of the image. The relevancy map, which is obtained in a zero-shot manner, is used as input to single image segmentation method. We can see in the last column the different segmentations for each query category. Specifically, let's focus on the crop view. Due to the effectiveness of the crop view, we aggregate it for different crops. The different crop sizes can be found in the supplementary material. So for the crop operation, we use the distractor class in order to generate a mean relevancy map, which shows the inherent noise of the interpretability method. For example, here we can see that the hand of the child is always with higher relevancy. Then we calculated the mean relevancy map, which shows the inherent noise of the model. And then by centering each relevancy map, by subtracting the mean relevancy map, we can see how we focus more on the child here, on the person. Then we see on the last row how we get a refined relevance map for the requested class, which is person. After obtaining the view averaged per category relevance map, which is of higher quality than the naive outputs of the interpretability technique, we still need a way to transform it into a discrete segmentation map. But yet, the refined relevance map are still not precise enough. Namely, segmentation typically spill over beyond object boundaries. Hence, we wish to transform the multiple maps for each point category into a discrete segmentation map, where each pixel is assigned with a one and only semantic label. We adapted two methods to use our relevance map as pseudo-supervision. First, we use a method for unsupervised segmentation, which treats the segmentation problem as pixel clustering problem together with the spatial continuity loss and feature loss. And we also used interactive segmentation technique. And in general, interactive segmentation guides the result of segmentation by interaction, where user provide boundary seeds or region of interest, bounding box, etc. For foreground and background. And we used the work of Constantine et al., which use region seeds as input. So now we have high accuracy relevance map, and we want to integrate it as pseudo supervision for single image segmentation techniques. So how we did it? We sampled the pixels stochastically as pseudo supervision using the following formula, where tau is a parameter, is a temperature parameter. In the case of unsupervised segmentation, we choose, for example, 100 pixels to be labeled as class 1, class 2, etc. And in each iteration, we sampled pixels again and again. And for the interactive segmentation, we sampled between 3 to 7 clicks, which we chose as background and foreground, namely class 1 or class 2, etc. The different experiments, parameters, and metrics can be found in the paper and in the supplementary material, together with the ablations. We evaluate our method on two benchmark datasets. First, we show the results on Pascal-Vogt 2012 validation set. First, we see a table A, where we compare our method to different methods that use similar amount of supervision. Next, we see at table B how we ablated different single segmentation methods, specifically unsupervised and interactive segmentation, with different parameters and different augmentations. Lastly, at table C, we compared our method to weakly supervised semantic segmentation, and we see that our method is quite competitive with other weakly supervised techniques, while being trained only for minutes. Namely, weakly supervised segmentation train networks like standard supervised segmentation, and our training is done at test time. So for each image, we take about half a minute or 1 minute, depends on the image resolution, to segment it. We see a similar trend also on the quantitative comparison on ImageNet segmentation, where we see that also with unsupervised and also with interactive segmentation, our method improves over the baseline in segmentation quality. We also see here similarly that interactive segmentation is superior to unsupervised segmentation. Let's see some baselines over a representative example from Pascal-Vogt. So here on the top row, left image, we see the input image, an image of a bird. Then we see here the relevance map as was generated by the transformer explainability method. We see that the bird is with high relevance values, but there is some noise on the background. Then we can see here that by thresholding the relevance map with the mean relevance value of the relevance map, we get desegmentation, which is with low recall. Here we can see the refined relevance map as was previously described with the test time augmentations. We can see here that the background noise is reduced and the relevance value of the bird are much more centered on the bird. Then on the bottom row, we can see the baseline of unsupervised segmentation without any pseudo-supervision, without a stochastic pixel sampling. We can see that although the unsupervised segmentation does not perform well on its own, combining it with the stochastic pixel supervision with the scribble that is given a scribble together with this relevance map, there is an improvement of the segmentation results. Then we can see here that the unsupervised segmentation together with the scribbles with the refined relevance map provides a much better segmentation. And we see here the refined relevance map, and we see here the segmentation results of interactive segmentation with the refined relevance map. Next, we want to show some examples for rare classes that we can now segment since we use a pre-trained language vision model that trains on internet scale data. So we see this read some rare examples. For example, we can see a dragon or big doll or E.T., mummy, flying car, etc. And we see the segmentation results now. And we see here how different long tail categories can be segmented using our method. More examples can be found in the supplementary material. In this figure, we can see another example of a special and unique visual concept, which is rare and we cannot gather a lot of data of it. Hence, we cannot easily segment it with the standard supervised segmentation method, which is landmarks. And here we see in the first and third rows the input RGB images, and in the second and fourth rows we can see the respective output segmentations. Conclusions. So we presented a simple and lean method for segmenting any object without pixel level annotations or multiple sample images. We showed that we can distill test time a pre-trained language vision network for semantic segmentation of any object. For future work, we can explore other combinations of segmentation algorithms and augmentations, which can further improve the segmentation performance. Thank you for your listening.